Hello students, today I am going to teach tautomerism. It's a very important topic in organic chemistry because you need the concept of tautomerism to understand reaction mechanism. Okay, so that is why it is very important. It is very important in organic chemistry to learn tautomerism. What it is. For most compounds, all the molecules have the same structure. Whether or not this structure can adequately be represented by a single Lewis dot structure. But in many cases, there is a mixture of two structurally indistinguishable compounds that are in usually rapid equilibrium. Like say this is A and A is in equilibrium with A prime, and A prime have their structures are nearly same. Okay, they are distinguishable. Clear? So A and A prime structurally they are distinguishable and they are in rapid equilibrium, and this type of phenomena is called tautomerism. Clear? Now first I will discuss proton shift tautomerism. First I am going to discuss that is proton. So first one is proton shift tautomerism. Is that clear? What happens in proton shift tautomerism? It's a proton in most of the case, in most of tautomerism, it's a proton that shifts one atom of a molecule to another. So actually in proton shift tautomerism, there is a, I can say that it is a 1-3 proton shift. Why I am saying 1-3 proton shift? It will be cleared after some time. Okay. First, in this category, that is proton shift tautomerism, first comes keto-enol tautomerism. Okay, this is the category 1. In this category, first comes keto-enol tautomerism, and that is very important. Okay, keto-enol tautomerism. Clear? In keto-enol tautomerism, what happens? Let's see. This is keto functional group. Clear? And I am marking this hydrogen by red color. Okay, now few minutes before I told you that keto-enol tautomerism or proton shift tautomerism, because this is proton keto-enol tautomerism actually subcategory of proton shift tautomerism. Clear? So and in this case I am trying to say that it is 1-3 proton shift. Why? See, this is 1, this is 2, this is 3. Now this high proton means this hydrogen gets transferred from the number 1 atom, this 1 atom to 3 atom. That means here it is in oxygen. So this hydrogen gets transferred to this oxygen atom, means this third atom. Clear? Just I am numbering in this way. I have numbered in this way. Clear? So when this hydrogen gets transferred to this oxygen, then there will be a oxygen hydrogen bond. Then obviously what will happen? Now this carbon has 3 bonds. Clear? Clear? This carbon has 3 bonds. We know that number of bonds arising from carbon should be 4. Okay, that is why there should be double bond. So the name of this compound is enol. Why enol? In IUPAC nomenclature, in stands for double bond and OH means all. Okay, that is why it is enol, means OH group attached with a double bonded carbon. Clear? So that is why it is enol and it is keto form. This is keto form, this is enol form. Now one question is very important. I think this question is knocking in your brain, knocking in your head, that which one is stable, keto form or enol form. This answer can be given from concept of thermodynamics, because we chemists learn thermodynamics to know whether the process is feasible or not. Okay, or whether the compound is how much stable than another compound, another compound. Okay, this kind of information we can get it from thermodynamics. Okay, let's see how we can say which one is stable, keto form is stable or enol form is stable. Okay, in keto form, bond energies, just I'm going to write down the bond energies, because here CH bond breaks. So bond energy of CH bond is 99 kilocalorie per mole. Clear? And here a new C double bond C bond is formed in enol form. So bond energy of C double bond C is 145 kilocalorie per mole. This CC bond breaks in keto form. So bond energy of CC is 83 kilocalorie per mole. Clear? And we have new CO bond. We have a new CO bond in enol form. So bond energy of CO is 80 kilocalorie per mole. And this C double bond O, it also breaks in keto form. And C double bond O, bond energy of C double bond O is 166 kilocalorie per mole. And here see, there is a new OH bond. Okay, in enol form. So bond energy of enol, bond energy of OH is 111 kilocalorie per mole. So these are the bonds break in keto form, bond broken and bond formed. So sum of bond broken is 348 kilocalorie per mole, and sum of newly bond formed in enol form, that is 336 kilocalorie per mole. Clear? So it is clear that keto form is thermodynamically more stable by 12 kilocalorie per mole. So this thermodynamical calculation, this thermodynamical calculation shows that keto form is 12 kilocalorie more stable. Keto form is more stable by about 12 kilocalorie than that of its enol form. Clear? Keto form is thermodynamically more stable by 12 kilocalorie per mole than that of its enol form. So from this thermodynamic data, it is clear that keto form or carbonyl form, because if there is hydrogen, if there is an hydrogen, then it becomes aldehyde. So it better to say carbonyl form. Carbonyl form is more stable than that of its enol form. But if you modify the carbonyl compounds in such a way so that it is possible that enol form, a percentage of enol form can increase. Okay, some modification in the structure of carbonyl compound can enhance the percentage of enol form. Okay, but how we can increase the enol content, let's see. This is butanol. Okay, it's carbonyl compound. Its enol content is very, very small, negligible. Okay, so total equilibrium is favored towards carbonyl form, and keto-enol tautomerism is 1,3 proton shift. So 1, 2, 3. So this, out of 2 hydrogen, 1 hydrogen will be shifted to oxygen atom. Here enol content is very, very small, that is percentage is 5.5 into 10 to the power minus 4 percentage. Percent is very, very small. Okay, nearly equal, it is nearly equal to 0, 5.5 into 10 to the minus 4. Okay, but if you incorporate, if you introduce methyl group or any alkyl group in this alpha carbon, then percentage of enol content increases. So this hydrogen will be get shifted to this oxygen because 1, 2, 3. Okay, 1, 3 proton shift, remember. Now the percentage of enol content here 1.4 into 10 to the power minus 2. This is the percentage. So it is clear that here enol content is larger than the first example. Clear? Now obviously why it is happening? Because here in this enol content only 2 hyperconjugative hydrogen. Okay, but here there are 5 hyperconjugative hydrogen. I have already discussed in my previous videos that hyperconjugative, if higher the number of hyperconjugative hydrogen means higher stability. Okay, so that is why due to hyperconjugation in here percentage of enol content increases. This is just because of hyperconjugation, because introduction of alkyl groups on the alpha carbon of the of a carbonyl compound increases the enol content, because in the enol content in the enol content number of hyperconjugative hydrogen increases. Clear? So reason is hyperconjugation. Clear? So hyperconjugation stabilizes the C double bond C in the enol form. Second one is, if you introduce aryl group on the alpha carbon of a carbonyl compound then also enol content increases. Clear? So let's see how. In this compound, percentage of enol content is very small, that is 1.4 into 10 to the minus 2. But when you introduce aryl groups in the alpha carbon of a carbonyl group, carbonyl compound, then enol content increases. So this is alpha carbon. Why it is alpha carbon? Because this is the next, this carbon is the next to the functional group, that is here it is carbonyl aldehyde group. This is phenyl ring, aryl group. This is another aryl group. No, one hydrogen attached to this carbon, alpha carbon. So there are two aryl groups attached to the alpha carbon. Okay, here the enol content is a good amount of enol content is good, that you can't neglect. Here it is 9.1%. Now why enol content increases? What is the reason behind this? Because here resonance is possible, electron delocalization is possible. How? Let's see. I am showing you. See electron delocalization. This electron delocalization stabilizes the enol content, and this type of electron delocalization is not possible here. This type of electron delocalization is not possible in the first example. Okay, so that is why if you introduce aryl group or in the at the alpha carbon of a carbonyl compound, then enol content increases. Next example is, by the introduction of a carbonyl group on the alpha carbon of carbonyl compound, the enol content increases. Okay, again I am telling you, by the introduction of carbonyl group on the alpha carbon of a carbonyl compound, the enol content increases. So I am writing this. Okay, so introduction of carbonyl group on the alpha carbon of carbonyl compound increases the enol content. Obviously I have to give example. Okay, I have to give an example, because without example it is the teaching is will not be complete. Okay, for understanding purpose, examples is 100% required, 100% needed. Okay, this is acetone or propanone. Now which carbon is alpha carbon? Obviously this is alpha carbon. Now I have told you that if you introduce carbonyl group on the alpha carbon, then alpha carbon of carbonyl compound, then enol content increases. Clear? So this is the alpha carbon. Now I am going to introduce a carbonyl compound, carbonyl group in this, on this alpha carbon. Okay, let's see. Clear? Here in this compound, that is propanone, the enol content is very small, negligible, that is only 1.5 into 10 to the power minus 4 percentage. (1.5 into 10 to the power minus 4). Okay, but here that is enol content, extent of enol content is very large. Okay, more than 50%. Here it is 76.4% enol content. Okay, again 1 3 proton shift, 1 2 3. So out of 2 hydrogen, 1 hydrogen will be shifted to this oxygen. Okay, so percentage is 76.4 enol content. Now why it is happening? So that much high enol content, how it is possible? What is the reason behind it? There are two reasons. First one is electron delocalization through or enol form is stabilized through conjugation. Second point is, no, so first I need to show you how conjugation is playing in this example. Two lone pair. Okay, so extended electron delocalization. This extended electron delocalization stabilizes the system. Clear? So first point was enol content stabilized through conjugation. Second reason is intramolecular hydrogen bonding. See, there is intramolecular hydrogen bonding. So there is an intramolecular hydrogen bonding present in the enol content, which stabilizes the enol content. Clear? So that is why the percentage of enol content is much higher in case of acetyl acetone. So name of this compound is acetyl acetone. Because this part is acetone, so another acetyl group is incorporated in the alpha carbon of acetone. Okay, so that is why the name is acetyl acetone. Clear? So there are two reasons. That is why the enol content, extent of enol content increases. Okay. We have already learned that why enol content increases if you introduce carbonyl group on the alpha carbon of carbonyl compound. We have already explained this thing. Okay, now we'll see what happens if you introduce ester group. If you introduce ester group on the alpha carbon of a carbonyl compound. Okay, I am talking about this one. So this is alpha carbon. Now I am introducing ester group on this carbon. Okay. Clear? So here enol content is small, and what is the name of this compound? The name of this compound is ethyl acetoacetate. Ethyl acetoacetate. Abbreviation is EAA. Okay. Here the enol content is very small. Enol content is in enol enol form. The structure of enol form is this one. So this hydrogen this alpha hydrogen gets shifted to this oxygen because 1 2 3. Okay, so enol content, this is the enol content. And the percentage is very small, near about 8%. But in case of this one, where I have introduced carbonyl group on the alpha carbon instead of introducing ester group, in that case we have already seen that the enol content is very high, that is near about 76%. So this hydrogen will be shifted to this oxygen, 1 2 3 1 3 proton shift. So why this is happening? Here it is 8% and here it is 76%. Why? So we can conclude that introduction of ester group on alpha carbon decreases the enol content with respect to introduction of carbonyl group. Okay, but why? So explanation is very unique, and this concept is also very important. Okay, so we need to consider the conjugation. We need to consider the resonance effect. Okay, let's see resonance effect in case of enol content of EAA, ethyl acetoacetate, means where I have introduced ester group on the alpha carbon of carbonyl compound. Okay, this is the corresponding enol form. Now, and obviously there will be intramolecular hydrogen bonding. This is intramolecular hydrogen bonding, and this intramolecular hydrogen bondings is present in both form, in both case. Like in case of enol content of first molecule, that is the name is acetyl acetone. Okay, and this intramolecular hydrogen bonding is also present in enol content of EAA. In both case, intramolecular hydrogen bonding is possible. Okay, so now first we know the lone pairs on the oxygen atom. Okay, so this type of electron delocalization is possible in the enol content of EAA. This is EAA, enol content of enol form of EAA. Okay, so this type of electron delocalization is possible. Okay, but in the same time, as this oxygen also contains lone pair, this oxygen also contains lone pair, so this resonance is also is going to happen. Okay, clear? So like two types of resonance. Okay, and this concept is called cross conjugation. Okay, this concept is called cross conjugation. So actually cross conjugation destabilizes the system to some extent. Okay, so one resonance, another resonance. Okay, so this is the example of cross conjugation. Cross conjugation ultimately destabilizes the system because here extended delocalization hampers. Okay, it affects the extended delocalization. So in enol form of EA, extended delocalization is not possible due to cross conjugation. Okay, then but in case of acetyl acetone, in case of enol form of acetyl acetone, extended delocalization is possible. Extended conjugation is present. Let's see. Intramolecular hydrogen bonding. This is okay. Now see extended electron delocalization. So extended electron delocalization. It is possible in enol content of enol form of acetyl acetone. Okay, so that is why enol content of acetyl acetone is higher than that of enol content of enol form of EAA. That means ethyl acetate. Clear? So take home message here. Take home message is that cross conjugation destabilize the system. Okay, it cross conjugation destabilize the system to some extent. Okay, if you have two molecules, in one molecule extended conjugation is present, in another molecule cross conjugation is present. So mind it, the extended conjugation will stabilize the molecule in a greater extent. Okay, now I'm going to discuss another factor which plays a crucial role in dictating the enol content, and that is steric effect. Okay, so this is number 5. Okay, so now for this I'm going to give you two examples. First one is acetyl acetone. Always I am saying that try to draw the enol content by yourself. Okay, that is 1,3 proton shift. In gas phase, the enol content of acetyl acetone is 91 to 93%. Okay, in gas phase, but in 3-methyl pentane 2,4-dione, it means here I'm going to here I have introduced one methyl group in the C2 carbon. Okay, in that case enol content drastically decreases. This is the intramolecular hydrogen bonding. Here in enol content is near about 42% in gas phase. Now why this drastic downfall of enol content for 3-methyl pentane 2,4-dione means here I have introduced one methyl group at C2 carbon. Okay, why? C2 carbon means if I consider 1, 2, 3, okay, but in according to IPSC nomenclature, methyl group is at number 3 carbon. Okay, now but why I am saying at C2 carbon, just considering this skeleton C1, 2, 3, these 3 carbon. If I consider these 3 carbon, then you can say you have introduced methyl group at C2 carbon, but according to IPSC nomenclature, methyl group is at C3 carbon. Clear? Okay, so see, when in the enol form there is a drastic steric clash between these two methyl group and between these two methyl group. This drastic steric clash destabilizes the system. Okay, so that is why enol content, percentage of enol content decreases when methyl group is introduced at C3 carbon, according to IUPAC nomenclature at C3 carbon. Clear? So this is one of the unique example where steric effect plays a crucial role in enol content in tautomerism. Clear? So reason is steric class. Clear? I'll show you later, don't worry. Now I am going to give you another very important compound, that is here enol content is not possible. This enol content is not possible for this bicyclo compound. Sorry. Why? Why enol content is not possible for this type of bicyclo compound? Because bridgehead double bond. This is bridgehead, this position, bridgehead position, and bridgehead double bond is not possible. Because double bond is planar, but this is not going to in a plane. These three atoms cannot be in a plane. Okay, these three atoms cannot be in a plane. Now I am showing you the actual geometry. See how, see this carbon, these three carbon is not planar, so that is why double bond is not possible here. Double bond is not possible here, so that is why enol content there for this compound zero enol content, like enol content is not possible, enol form is not possible for this compound. And this concept is very unique, that is bridgehead double bond is not possible. Number 6 exam, number 6 point. This is 1,2-dicarbonyl compound. Clear? So here enol content is very less, like for this compound enol content is very less, like near 0%, 0% enol content. Enol content is 5.6 into 10 to the power minus 3%. So okay, it's very small. Okay, but this is also 1,2-dicarbonyl compound, but here enol content is 100%. Here enol content is 100%. Here enol content is to some extent 100%. So why? Now I am going to explain. In the first example, these two vicinal carbonyl groups, in the first case, there is severe dipolar repulsion between the two vicinal carbonyl groups. Okay, severe dipolar repulsion. Oxygen is electronegative, so here we will have a two dipolar dipoles, and obviously dipolar repulsion is present, and now as there is severe dipolar repulsion, now this compound will rearrange in such a way so that dipolar repulsion will be minimized. How it will minimize? It will rotate by 180 degree. In anti-orientation, here the C double bond groups are in syn orientation, but in anti-orientation the dipolar repulsion is cancelled out, gets cancelled with each other in anti-orientation. Clear? So that is why enol content, and that is why keto form is very more stable. The keto form is more stable than enol form because here a syn form gets converted into anti-orientation. In anti-orientation, it is very stable. Clear? Now I am going to show you how rotation is possible. So these two carbonyl groups are in the same site. So these are syn orientation. Now 180 degree rotation is possible. Clear? See. Now this C double bond C double bond O, these two C double bond O are groups are at anti-orientation, are in anti-orientation. So here in anti-orientation, dipolar repulsion gets cancelled out. Two dipolar repulsion gets cancelled out. Clear? And why dipolar repulsion gets cancelled out? Because angle is 180 degree, so mu resultant will be mu1 square plus mu1 square plus 2 mu1 mu2 cos 180 degree. We know cos 180 value of cos 180 degree is -1, so 2 mu1 square minus 2 mu1 square, it becomes 0. So resultant dipole moment is 0. So that is why this keto form, this anti-orientation is very much stable. But in case of the cyclic compound, this anti-orientation is not possible. Clear? Because in here the two carbonyl groups are locked in syn orientation. Because it is cyclic compound, these two syn carbonyl groups are locked in syn orientation. So to escape dipolar repulsion, it goes over to the enol form. Clear? So that is why 100% enol form. Here enol form is 100%. So it tries to minimize the dipolar repulsion. That is why it gets converted into corresponding enol form. Clear? And evidently here the enol form is also stabilized through intramolecular hydrogen bonding. This intramolecular hydrogen bonding. I think it is clear now. Now I'm going to show you another example. This molecule. Here enol content is not possible. Just think why enol content is not possible. Now let's consider what will be the enol form. This is not possible. Enol form is not possible, but I'm drawing the enol form. Clear? Because in enol form this one is very much, this keto form is already strained, because 4-member ring is already strained, and this is 4-member ring, but there is a double bond in the 4-member ring, so it becomes more strained molecule. It becomes more strained molecule, as another sp2 atoms has to fit into 4-member ring. Clear? And if you consider the dienol form, this is not all. Dienol form is also not possible. In dienol form, 2 double bonds in the 4-member ring, and additionally the number of pi electrons here 1 2 3 4 4 pi electron means, and it is, so that is why it is anti-aromatic. 4 pi electrons over a monocyclic ring is anti-aromatic system. So anti-aromatic system is very less stable. Clear? So two effect. One is anti-aromatic effect and 2 double bonds in the 4-member ring, which is very strained system. Clear? So that is why enol content is not possible for this compound. Now I am going to give you another interesting example, that is examples of keto-enol tautomerism. I think all of you know about phenol. It's an aromatic compound, and but here tautomerism is also happening. So can anyone tell me what is the keto form of phenol? This is phenol. Here I am going to draw only one hydrogen. Okay, I am drawing the all hydrogen here. Usually I don't draw the, so the all hydrogens in phenol. So just try to draw the keto form of phenol. I told you that it is keto-enol tautomerism is 1,3 proton shift. Okay, see, this is 1 2 3. So this hydrogen gets shifted to this carbon. So keto form will be this is a keto form. This is transferred hydrogen. This is oxygen. So now there should be double bond. Clear? This is keto form. But as we know that C double bond O is more stable than that of this C double bond C. So that so you can say that keto forms. So according to this data, according to this thermodynamic data, that is C double bond O is higher. C double bond O bond energy is higher than that of C double bond C. You can say that keto form is more stable than that of enol form. This is enol form. This is keto form. But here phenol is additionally stabilized by resonance. We know resonance energy of benzene is 36 kilocalorie per mole. So that is why here enol is more stable. This is the stability order. Clear? But now I am going to give you another example that is also very interesting. That is 1,3,5 trihydroxybenzene. Here you are expecting that enol form is more stable than that of keto form, but here keto form is more stable than that of this enol form. This will be the keto form. Try to draw it by yourself. Okay, it's very easy. This is keto form. But now why this keto form is more stable than that of this enol form? This is keto form. This is enol form. here stability order is reverse. Now why here keto form is more stable than that of its enol form? Here there are 3 C double bond O. 3 C double bond O bond energy data is more stabilizing than that of this resonance effect of benzene. So that is why actually C double bond O bond energy exits over resonance stabilization coming from resonance. Clear? So that is why here here keto form is more stable because here 3 C double bond O. Stabilization from this 3 C double bond O is very high. It exits over stabilization coming from resonance. So that is why in this case keto form is more stable than that of its enol form. Clear? Now I am going to give you another example. They are now this is not keto-enol tautomerism. It is something. It is different. It is tautomerism, but it is nitro acid tautomerism. Nitro acid tautomerism. What is this? Aliphatic nitro compounds having alpha hydrogen are in tautomeric equilibrium with acid form. First, I am going to draw the aliphatic nitro compound having alpha hydrogen. Suppose this is nitro group. Then this carbon is alpha. This carbon is alpha carbon. So it has alpha hydrogen. Clear? Now again 1,3 proton shift. Now this proton gets shifted to this oxygen. This oxygen. Clear? Now I am drawing the resonance canonical form of this nitro form. It is very easy. Clear? So acid form will be this. This is the acid form. Clear? So this hydrogen gets transferred to O minus. This is acid form. This is nitro form. So it is clear that nitro form is stabilized through resonance. So that is why nitro form is more stable. This nitro form is more stable than that of its acid form. This is stability order that you need to know. It is very small information, that is nitro form is more stable than that of its acid form. Clear? So because nitro form is stabilized by resonance. Next example is nitroso-oxime tautomerism. Nitroso compound. This is nitroso compound. It has one alpha hydrogen. Clear? This is alpha hydrogen. This is alpha hydrogen. Nitroso compound can tautomerize with the transfer of a proton from carbon to oxygen to form oxime. Clear? So this hydrogen is now going to transfer to this oxygen. Clear? So oxime form is that we need to give a double bond because carbon is tetravalent. So this is oxime. This is nitroso form. This process is exactly like enolization of carbonyls, but here it uses N double bond O. N double bond O group instead of C double bond O group. Here the equilibrium will try to remain towards oxime form. Because why? Because we know, like, when delta H is negative, then it is like process is feasible. We know delta H in a reaction is summation of bond energy of reactant minus summation of bond energy of product. So here in the reactant, bond energy of EC double bond N, so sorry, in product EC double bond N, and here new NO bond plus ENO, and there is a new OH bond. So OH bond is more stable than that of here N double bond O plus ECN plus ECH. So as bond energy of product is higher than that of bond energy of reactants, then obviously this delta H becomes negative. So process is feasible. So that is why here oxime is more stable than that of nitrosulfone. So here oxime is more stable than that of nitrosulfone. So this process is exactly here the equilibrium will try to remain towards oxime form because oxime is more stable than that of nitrosulfone. Now I am going to show you another type of tautomerism that is also very unique. So it is called Valenced Automatism. Okay. This is COT abbreviation, means cyclo octa tetraene 4 double bond. Clear? Cyclo octa tetraene. Its tautomeric form is, this is the tautomeric form. This is called Valenced Automatism. This is generally understood as a shift in interatomic distance. So this interatomic distance becomes smaller, these two. Again I am telling you, this is generally understood as a shift in interatomic distance within a molecule without the separation of any atom from the rest in any intermediate stage. Okay, so by arrow notation I can show you in this way. That's it. This is Valenced Automatism. Okay, now I'm not going to explain in details of Valenced Automatism, that is beyond your limit, but try to memorize this example. This is very unique. This is one of the unique examples of Valenced Automatism. Clear? Again another type of tautomerism, examples of tautomerism, that is ring chain tautomerism. So here usually combining proton and valence type is called ring chain tautomerism. This type of tautomerism can occur when one functional group of a bifunctional molecule attacks the other with its pair of electron, thus forming a ring with a shift of proton. Now so this is a bifunctional compound, hydroxyl group and aldehyde group. Okay, hydroxyl group and aldehyde group. This is the proton. Now here one functional group, this functional group attacks carbonyl functional group, carbonyl carbon. Clear? So this hydroxyl group contains lone pair. Now this hydroxyl group attacks the carbonyl carbon. Clear? It will attack this carbonyl carbon. Thus, then there will be form a ring. Obviously, there will be formation of ring like this, and additionally, there will be shift of proton. This proton gets shifted to this oxygen. Let's see. Clear? I'm marking this oxygen by green. It will be better to understand. Clear? This is the new bond. Then 1, 2, 3, 4, 5, 6. 6 member ring. Clear? Now O, and this hydrogen, as this hydrogen gets shifted to this oxygen, so actually this is hemiacetal. I will obviously I will post a videos on acetal and hemiacetal chemistry. That is very unique. So now this is the ring chain tautomerism. Here now I'm going to end the Automotism lecture, this long lecture. Okay, I think you have all enjoyed the Automotism lecture. So if you have any confusion, then write in the comment section, or you can mail me, or I have given my link of Facebook page in my YouTube page. So bye. Okay.